latest selection of the newest semiconductors and electronic components. So let's get to our keynote. Christopher, thanks for being here today.
Thank you for having me, Daniel.
When I think about who in my brain worked on Siri and made that a thing, I think of like researchers who had been doing machine learning since they were, fresh into grad school. But I hear that's maybe not the case for you. Could you give me some background of, how did you start in the world of tech and how did you get into the AI ML side of things?
Okay, so yeah, getting into tech, that probably started when I was about 8 years old and, at what was the Timex Sinclair 1000 little tiny computer there, and then eventually graduated to a VIC-20 Commodore. So I was rather of modest economic means, so I couldn't get the Commodore 64, so I had to kind of work on lower memory. But it was really cool with the Commodores. They had these things called sprites, so you could get into doing computer graphics stuff using vectors, which was pretty cool. Learning how to do vector programming, I mean, we had to use MachineMon back in the day to just know where every single memory bit is available at any time to get something out of a machine with very little as far as resources go. So yeah, kind of in constrained environment. So that was fun. But yeah, so I wanted, I think, to be an engineer and a computer scientist and everything, and that didn't work out with my father, who said, you're going to be a doctor or a lawyer. You're going to be a doctor or a lawyer. There's nothing else, A good Catholic Jewish kid like me, you gotta be one or the other of those, right? And but think of all the different options. I was told, you could be a defense lawyer, you could be a prosecutor, you could be, a plaintiff lawyer doing car wrecks. Think of all the different career possibilities, and you could be a pediatrician, an oncologist. What else would you want? So I ended up becoming kind of both, and none of the above in my career. That's kind of fast forward it, but I ended up in Japan. Where I was a grad student in medicine, working on immunology. Really, structural biophysics, if you want to get geeky about this, is what I was doing. The structure of these immune molecules and how they bind and the molecular dynamics of that. And so on this is in the 90s, early and mid 90s, where we had the old Indigo machines, if you remember those. And that was like a really powerful workstation at the time. Now today it'd look like something that's in your iPhone. But we were able to do some pretty cool stuff with that. I did a lot of the wet lab, mass spec stuff. And while I was going to medical school as kind of a side hustle, I started one of the first web design and networking consulting companies in Japan. Kind of, if you remember Razorfish back in the day, it was kind of that kind of a thing. So we designed websites, did network consulting, and some programming work in the very early days of the internet. Really as a side hustle, because people were asking me to do my own work in bioinformatics, I had to learn how to program Perl scripts and CGI scripts back in the day, just to do my own work on sequence stuff, which is what I was working for. And then people said, oh, wow, you know how to do HTML programming. Hey, can you do a website for me? And can you do a website for my uncle who runs this blah, blah, blah business? I'm like, guys, I got to start charging money for this, come on. And I did. And so we got together with a graphic designer and another guy who kind of knew the finance things. So a company called Webula, eventually it became AppMark. Had that going for me as a part-time gig on the side, but we ended up taking Jafco, one of the largest VCs in Japan, money because the company was growing. This is mid-90s, before .com really took off, and had a profitable business. And so that was my first foray into technology in the early days of the web. One of the guys was a graduate student in the computer engineering department there, was a British-Iranian dual national student in grad school in Japan, Baba Kojed, who now runs AI over at Cognizant. And so I initially hired him to work on some gigs that we had at that company. And when we started talking about things, we had an opportunity where we had won actually a large engagement with a company in the local area in Fukuoka, Japan. And we were at a celebration at an izakaya, one of these little Japanese pubs. And the mama-san who runs the pub, the owner, we wanted her to put on the baseball game. and baseball's really popular in Japan, as you know. And she's like, she couldn't get the thing to work and to change to the cable and then this thing. He said, "Hey, son, put on the baseball game." And he got up there and 2 seconds later had that. And it worked. I want one of those. I want one of those agents like that. To pop up on the screen and say, "Hey, son, get me the blah, blah, blah." And we were thinking, like, wouldn't that be great? These were the days of the VCRs. If you ever tried to record something with a VCR back in the day, it was just horrible. There was no interface. It was like, touch this 3 times. Like, it's like setting an analog alarm clock, you know? Oh, crap. And you would always try to record the baseball game, and then you get home and you had recorded like Days of Our Lives or something, you know, because it was just a horrible interface. So we're like, you know, if I could just say, "Hey, record the baseball game tonight," wouldn't that be great? And so that was kind of the thing. And then, you know, I was working on what now we would call small language models in my work, in machine learning, in proteins, amino acids. And I knew that Babak was working on this artificial life thing with all these kind of symbiotic agents that were in this genetic algorithm kind of world. And I had said to him, like, you know, maybe, you know, this agent thing on the big scale of an agent to do something for you was one thing, but agents as small little devices was another thing. And so I said, "Hey, Babak, do you think you could use the artificial life stuff to go after this natural language problem? And we could have something really cool here that people want." And initially he's like, "I don't think you get this. Natural language is a really hard thing." And no, I think I kind of get this. But he came back later and said, "Yeah, you're right. Okay, let's try to do this." So we ended up basically embedding small language models, tiny language models inside these agents that worked symbiotically in an ensemble to solve a bigger problem. And that was kind of how we got started with that idea. It eventually became a company that got sold to Sybase, and then half the team, including Adam Chire, was at that company, to the Kalo project, which was part of a DARPA program that the company was involved with. And then it got developed a little bit further. Voice recognition got a lot better. Our mobile devices got a lot better over those years. And then, you know, 7 years later, it ended up as a product. And before it was launched as Siri, the company, Apple bought the company, bought the application, and then embedded it into the iPhone. That was the story.
That is quite the journey, though, from, you know, biophysics and wanting to watch a baseball game into arguably what people would think of as the premier and initial, you know, voice recognition AI chatbot sort of system.
It was the first one. I mean, we literally had the equivalent of Alexa as a demo running in our little office in Mountain View on Castro Street above the Indian buffet restaurant. In 1998, we were able to say, record all the World Cup soccer games that include Germany, for example, and have that happen. And that's 1998, you know. And it was kind of interesting, you know, people did have those expectations, kind of like they think ChatGPT should be this omniscient, godlike thing. They thought, well, why can't it do this? Why can't it do that? Because we didn't program it to do that yet. You know, it handled very small domains pretty well. Really good. Even today, I would say Siri is arguably best at what it was designed for, which is device control, setting alarms, setting the clock, that stuff that does really, really well. Answering ambiguous questions, maybe not so much, right? But the expectation was so high out of these systems, right? People would come in and think, you know, that it should be able to shine my shoes and, you know, do all these other cool things, and it should answer any question under the earth. And we don't expect that of other human beings, never mind some kind of a chatbot or an agent. So it's kind of interesting, this kind of human behavior that we want that system to do so much more than its capabilities. And we get really disappointed really quickly when it doesn't do everything that we want. And I think we're seeing that a little bit with AI right now. You know, it's like, oh, this thing should do everything and answer every question perfectly without hallucinations and whatever. And, you know, this is engineering. It's computer science. It's not actually creating life and people and intelligence. You know, it's an artificial substitute of not really good intelligence is the way I think about it now. Maybe it'll get better and better, but it's unintelligent intelligence in a lot of ways.
Yeah, it's a very interesting challenge to think about. AI today, you think of ChatGPT as being kind of, in the general public's mind, kind of an end-all be-all. mostly because the way we perceive intelligence as humans is often through interacting with other people in language. Can you talk about specialization of AI and how maybe a large language model might look different from something that's trying to figure out a different way to like fold proteins and create a new medicine?
Yeah, I think that there's been this expectation that we're going to create one model that rules them all. And I think Babak and I have now, if looking at his work over at Cognizant and my work, I think that we're coming kind of full circle in this idea that it needs to be this one omniscient big thing. When actually models do better when they're specialized, just like humans do, right? You think of an orchestra and the different roles there. You know, you don't want the conductor playing flute necessarily, and you don't want the drummer to get up and try to play trombone or French horn or something like that, right? In a large band. But each of these specializations together can make a really beautiful orchestration of things. I think orchestration systems is something we hear about a lot in engineering and software engineering. And I think we don't design a massive monolithic piece of code anymore. We've had object-oriented programming for a long time. You want things broken up and specialized because it's easier to maintain, easier to upgrade things in a modular way. Artificial intelligence systems should be designed that way. We should design a system that's really good at visual imaging for this, or really good at this particular task, or protein folding. You know, nobody uses the protein folding AI that did the protein folding stuff at Google there to answer pop quiz questions like ChatGPT. You don't use that to write new lyrics for an album. You don't use it to design music. You use it to do protein folding, right? And you don't use DALL-E to build a bridge. It'll design a bridge, but probably not one that'll work really well. So this kind of granular specification, specialization, and then working with those different models as an ensemble of models together that, just like human organizations, get together and I can do this, I can do that, I'm really good at this. And having them interact and having models work with other models really, I think, is kind of the future. When Babak and I envisioned, how these agents would work together, we thought of them as they could be the fundamental objects that would interact, even in an operating system. And in areas, just in the software engineering sense of this, beyond just natural language understanding, but even as software objects, being semi-autonomous, small pieces of intelligence that together can create a larger intelligence, just like human beings can in organizations. So that's really kind of the vision that we have, and we're starting to see this coming full circle. You're not going to use ChatGPT to, like what we do with Andretti Global in the IndyCar races, to predict a slip angle. It was really funny. Eric Bretzman came to me during one of the races about a year ago and said, "Oh, we can fire Zapata now." "Oh, really?" "Yeah, we don't need you anymore." Because I got the $20 a month version of ChatGPT, so we have generative modeling. We don't need Zapata's expertise here. "Oh, really?" "Yeah, I asked ChatGPT how to win the Indy 500. And I said, "Oh yeah, what did it say? Go fast?" No, much more specific. Don't crash the car was number one. And the second one was qualify in the top 10. Great generalized answer, right? Didn't tell me what damper setting I need to use or how much front wing I need to put in there or whatever. It's not going to give me an engineering answer of how to actually do that. But it's great at summarizing. So ChatGPT, these language interfaces are great as UI tools to use natural language to summarize things. But they're never going to give you an engineering answer, right? They're never going to build a bridge or design what slip angle I need to use to go around the track, or do something, what trajectory my rocket needs to go at to launch a satellite into orbit. You can design models that do that and have this natural language interface doing what it does best, which is use language to communicate results. So I think that these models being used for what they're good at is really the future.
It's almost a world of like loading libraries and calling functions, but instead of calling functions, you're calling specifically trained AI agent.
a little bit smart object, really. If you think about it that way, that's really, kind of the way to think about these things. If you're using them as an engineering system, well, you will basically have an object, but the object is, has its own code and its own model inside it to be able to do a specific task really well, semi-autonomously.
I'm curious, you've seen a lot of different applications of AI. I know you spent some time at Nissan doing like battery prediction. Can you tell me a little bit about that part of your career and what you learned and how that kind of built into what you're doing today?
Yeah, in automotive, I was in the enterprise architecture there, and we brought in the first Hadoop stack in the automotive industry, actually, where we collated a lot of different information. We had information about the vehicles themselves, a bunch of autonomous driving information, battery information, battery predictive. So we created some things that went to production, like battery predictive analytics, to try and be predictive about what, range anxiety is a big thing in electric vehicles. And we had the electric Leaf vehicle. Being able to be predictive of that, saying, no, you're going to be good for this much, depending on how much you're using the air conditioning, how much you're using this and that, or how much you're in Silicon Valley on Highway 101, stuck in traffic, is something that people cared about. So, using AI as an assistant, and using data-driven, machine learning-based algorithms to kind of tell us how things were going, to be able to do things like predictive maintenance in the factory, to do predictive maintenance for cars, so that, people get really upset when they find out that something broke and they didn't know it was going to break, and they could have prevented that. You can prevent people switching brands of cars a lot by being proactive and telling them, hey, you might want to be taking this into the shop before they have a problem, rather than after. So these kind of things, using data and using data-driven stuff in the automotive industry, I think is really important. I think it's kind of informed some of the stuff that we did. It gave me street cred when we started working with the Andretti racing stuff. I've been interested in cars my whole life, turning a wrench since I was 8 with my uncles. So it was really cool to be working in a car company. I'd always loved cars, particularly working with the electric vehicles and these really performant systems. And then applying that now and applying the stuff that we're doing with AI in our interactions with Andretti Global, one of our key customers, and some of the work we're doing with optimization that we published with BMW as well. So this really important vertical that I think can gain a lot, as will many manufacturing industrial companies gain from the insights that you can get from these engineering models.
It's an interesting thought about even predictive maintenance for a car. We have 2 cars, and one of them, the AC compressor went out unexpectedly. And then the other one, at 200,000 miles, the steering rack went out. It's like, I happily wrote a check to get the steering rack replaced, but for the AC compressor, I was unhappy, even though they were about the same dollar amount, mostly because I knew one was coming and the other one was a surprise.
Yeah, I mean, there is a psychological thing about this. If you know you're going to have a problem and you can predict it and you prevent it before you break down, you feel better about that. It really was something we found in consumer behavior that happens to be the case. People don't like surprises at the end of the day. They don't like outcomes that they hadn't, predicted would happen. People don't have a problem that, my tires need to be replaced, unless it's a nail that they ran over that they weren't expecting, right? Then they feel really upset about the one tire they're replacing and not the 4 that they have to replace because they've worn out, even though the latter is more expensive. I think that this is the case with a lot of human behavior. If we can predict a disruption in HR in a company, right? If we knew someone might be leaving, we might do better at retention or better at succession planning, for example. So these AI systems are really going to become better, I think, at making us do what we do in companies in a more predictive manner and have, I think, fewer surprises, right?
My brain immediately went to, how do I send signals to my company's AI that I might be leaving soon and need a raise?
You probably are. If you're from your behaviors. No, I mean it. I mean, these the big data systems, what if we had all the data in that Hadoop system, it's kind of creepy what you can learn about behaviors, when you aggregate things over time, how things are reacting, they become very predictive of things. I mean, there were things that we could predict about a person just from their driving habits, about what might be actually going on in their life. Just because of their acceleration habits and braking habits. And you see these changes, you say, okay, something's Houston, we got a problem here. And we have to be kind of careful about that, because you're a consumer facing company. Do you want people to know what we know about them? Not really, So how do you do that? So, having the legal background there was kind of interesting, because it's like, okay, there are some privacy issues here. And there's also some PR issues that you have to think about. But it is true that when you aggregate that much data about people, you can actually predict what's happening. You can actually, there's a certain pretty good percentage. Like, we're predicting yellow flags, accidents on a track, and we're doing that with over 80% accuracy. Now I can predict when somebody looks like their behaviors are that they're going to leave their job, or they're going to at least be entertaining interviews in other places. You can actually predict that kind of stuff, for good or for bad. It is something that we have to think about, and I think that's why it is important for not just the scientists and engineers, but the ethicists, the legal people on this, to start thinking about what a world that includes these intelligent sources that have maybe better insights into what's happening than humans could have in the past, right? What does that mean? What are those implications? How do you run an organization when you do have that data? How do you use it or not use it? How do you prevent yourself from using it, or prevent it from being used in the wrong way? Now, I'm not one of these doomsday people who's like, oh God, the hell's going to take over and it's going to destroy the earth. I don't really think that we're really there, or that general artificial intelligence is a existential threat to humanity right now. But I do think it behooves us, just as we've had in every technology revolution, to have people starting to think proactively about what could happen, the what ifs. Because we've done a really poor job as humanity sometimes in understanding the maybe unintended consequences of having a good thing in technology, right? What's it going to do to human organizations and behavior? So I do think we have to start looking at that.
Yeah, I think history tells us tech is always pushing ahead, and we have to be very careful that it doesn't become exploitative. Like, having regulation and mindful usage progress along with technology is a huge opportunity for us as a race of humans that we need to be aware of. I also like the idea of my car saying, hey, you're braking a little hard today. Maybe move up that therapy session.
Yeah. Might want to slow down on the caffeine there. Switch to herbal tea today.
Yeah. You've brought up Andretti and F1 racing a little bit. Let's nerd out on that for a moment. What are some of the interesting or surprising ways that AI is making F1 racing better?
Yeah, I mean, we're in the IndyCar series, which is the American version of F1, where we are doing open wheel racing. In motorsport, really, it's all about strategy. It was funny when I took my son over to a race. He was never into racing, wasn't his thing, but I dragged him in there because he could go to a punk concert before that with Colton Herta, who plays drums as a side gig. That's how I got him there. But then when he saw what we're doing in the rack, and he saw how the drivers are interacting and looking at all the data and all this kind of stuff and what people are talking about, he's like, wow, this is more like the strategy games I like to play, like Risk and that kind of a thing. This is really, it is all about chess and strategy, and what are we going to do on our tire strategy, what are we going to do on our pit strategy, what are we going to do here. And I think that's really surprising to a lot of people, is just how data driven the sport always has been, because you need to conduct, it's an engineering contest is what he said at the end of the day, and that's what it is. It's an engineering strategy contest more than it is a driving contest. Yeah, I mean, the drivers will argue with you and say that, what they're doing athletically is pretty phenomenal, and it is. But if you get the strategy wrong, you can be the fastest driver on the entire track, and one yellow flag at the wrong time, like it just happened to Scott Dixon this past weekend. He missed on the strategy, went to the back of the line. He went from being in contention to win the race to not even having a chance. And so there really is a lot of data, a lot of engineering analytics that happens. It's a big data type of a game. And the AI piece of it is giving strategy and driving better decision making at the end of the day. This is about using AI to do better decision science, right? When should I pick this car? When should I not? What are the consequences? This is a statistical game, and AI, machine learning, is all about statistics and learning from the past and doing that. So we're able to take 20 years of historical data going around that track with various drivers and various circumstances, and then get very predictive about how things will happen. We also have, in that circumstance, really good physical models to start with. Physical models meaning simulators, right? Digital twins. In racing, the digital twins are really, really good. Like you've seen Gran Turismo, like if you get good at doing the game, that actually translates sometimes really well to doing it in the actual car. Because the digital twins, the games are, sometimes down to the millimeter level of tolerance on how well we know that track and what the track temperatures are, and the models of the cars are like perfect physical models of the cars. Like, so then you get into one of these simulators with the hydraulics, and it is really that thing. Like basically it's so predictive that if I take Max Verstappen and I put him in his car, in his setup for the Spa track, we can predict within 1/10 of a second what his lap time will be, and he'll drive that lap time in that car, just like he would on race day. With that setup. Okay, full fuel at the beginning of the race, what's your lap time? Qualifying setup, what's your lap time there? And it'll be within 1/10 of a second. That's how good they are. But what this means is that we now have this digital twin capability to actually, and all of the historical data, to do some things that you just couldn't do before. Because I can't tell Max, please sit in that simulator, and I want you to do 1,000 hours without eating and without sleeping in a row. We can't do that. He's kind of expensive too. But even a second-rate driver is not going to be able to do that for me.
Sure.
And I want you to do another 1,000 hours with these settings and another 1,000 hours on this track with that settings. You can't do that with a human being. But since we have a model of Max for what he does in the car, the hyperparameterization, if you will, and you can apply that to a near perfect digital twin within 1/10 of a second tolerance, I can now create synthetic data of 1,000 hours of Max sitting in that simulator with different settings, different things. I can do it 1,000,000 times if I have enough money for the GPUs, right? And that gives us, I hate using the word synthetic data because it's actually just like having Max sit in that car and do 1,000 laps, which he can't physically do. But with that data now, we can build even better models. So this becomes really iterative. And we can get much better at predicting what will actually happen with any given driver on any given race. And predicting physical properties like the slip angle when you do this, when you do that. And therefore what the tire degradation is at a better level of fidelity than I could ever have done before. So generative modeling combined with the physical models that we have can really create this great iterative virtuous cycle where we get better and better and better at being predictive of about how things are going to happen, and therefore get better at this strategy game of what should we do.
Yeah, and that's where the interesting thing about racing is there's so much engineering that goes into it, but at the end of the day, it's the human factor that can make or break it.
It is. I mean, but the engineering itself is just really cool. I mean, the
marvelous
things we're able to play with, this is, aerospace engineering on a track. It really is. I mean, cool thing about the Indy cars is they weigh about 1,700 pounds now with the hybrid that they put in there. But if you were to turn that car around, right, because the wings have so much downforce, if you were to turn that upside down, put it on the ceiling, and run it at half speed, meaning about 120 miles an hour as opposed to the 200 that it usually runs, it would actually stick to the ceiling and crawl around like an ant. That's how much downforce those wings have.
Whoa.
So the engineering that we're actually accessing there, and it is just, it's phenomenal. So it's a lot of fun for people who are really geeky about, the physics and the engineering there. We get to play with this at an edge that you wouldn't get in an OEM car situation. And the cool
Sure.
thing is when we do things on the edge like that of what's possible physically with these machines, that all feeds forward into eventually into the OEM cars and the cars that we drive around daily to make safer cars, to make better performing vehicles for
Yeah.
consumers as well.
Yeah, I mean, my daily is a 2006, but it has like adaptive hydraulic suspension, big SUV, and when you turn it, it like the shocks on the right side get a little firmer, and
Yep.
that's
I mean,
got to
all of
be
these things, I mean, there's a lot of technology and modeling that goes into anti-lock braking,
yeah.
and all of this stuff happened first at the track. Yeah, the interesting thing that I learned getting into Indy was that the rear view mirror was invented at the Indy 500.
Huh.
Yeah, they used to have two people in the car, and they would have one person as a spotter saying, "Yeah, you're clear to go right." And then one day somebody's spotter didn't show up. He put a mirror on there, and he could race with only one person, so half the weight, and he won the race. And so
That's crazy.
from there on, everyone used rear view mirrors. So a
From
lot
that
of these
moment.
inventions, anti-lock braking to the rear view mirror, are coming out of auto racing, which is kind of cool for from an engineering development perspective.
That's wild. Keynotes for Industry Tech Days are sponsored by Mouser Electronics. As your design fulfillment distributor, Mouser is your authorized source for millions of components from thousands of leading brands. Come discover, design, develop. Let's talk about some other applications where this is really interesting. You've been working in grid management. It's maybe not quite as like flashy as racing, but also we all need it and use it. Can you talk about what that application kind of looks like and maybe some of the surprising areas where we're seeing an improvement in grid capability?
So, in any of these kind of networked situations, if you think about what we're doing in racing with the yellow flag prediction, we can actually predict ahead of time that there's going to be a problem, there's going to be an accident. So we take 20 years of data and we start to see things in the data, like when cars get really close together, or there's a pit cycle, or these kind of things, and some things that are more nuanced. There is a higher chance that there's going to be bad juju here. And so if you think about this in the telecom network space or any other kind of grid management type of a situation, if you were to have one of those yellow flag predictors at every network hop or every node of a power management system, and you see things are kind of wigging out here because demand is too high or whatever, and you're able to send before things go down that signal. What you end up with as the person managing that network when things do go bad and everything starts to collapse is, instead of just getting these 100 devices are down and here's the hierarchy of those devices, roll 100 trucks and go figure it out. Okay, now what we can do is, we've had, prior to the final calamity, we saw, okay, something was happening here. What was happening here first? Okay, Taylor Swift just dropped a new video on X, okay, and that created this problem. Okay, but it started happening at this router first, and then here, and then here. So when we roll the trucks, we can actually now say, you know what, try here first, try there, try there. Instead of rolling 100 trucks, we can roll 3. Same thing with power outages. We are having a big demand signal over here because there's a weather event, heat, whatever it is. Lightning strikes to this transformer over here. Where do we go first to diagnose and mitigate? And right now, working at Verizon previously as a network operating ops guy, one of my other gigs that I had, really you just get these 100 devices are down. Go figure it out. And you know which one's related to which one, but you don't have that predictive information ahead of time. If we had that predictive information, we can be much more targeted, much more effective, much more cost-effective and time-effective in getting the network back up and running. And so that works. That kind of concept works in telco, in power grid management, in any kind of IoT application that you might imagine on the edge. And that's a really cool application of this technology.
So if I wanted to apply this to a specific problem I had or to my industry at large, making widgets, where would I start? What questions would I ask? What considerations or data should I start to gather to actually get to a useful end state?
Well, you said something really interesting there, and this is what we found with model development that people assume is the first step. Go get the data, and what data do I need? And that's where people have started from the old big data days. That's what we were doing at Nissan. Okay, let's just get all into a Hadoop thing, and then we'll figure out what it means later. And what we found in our engagements at Zapata is that we kind of have to turn this paradigm on its head. We really have to start with the decision science. What do you want to know about the world? How can I make your business more efficient or solve your problem? What problems, if I solve them, would really move the needle for you, right? And if you start there and then you say, okay, yeah, this, I want to predict yellow flag so I can make a better strategy decision, to go back to the racing example, right? Okay, what model would I use to do that? Okay, we would use a GAN model that could do this and blah, 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 and be predictive of that. We'd use reinforcement learning here with the, okay, what do we need that? Well, we need some data on this, this, and this. Now I can go out and say, what data sources do I have? And if I don't have them, what synthetic data can I bring to the table? What other data sources can I in-license or get access to be able to build that? So it actually kind of turns the paradigm on its head, where I'm not just storing data without thinking about it, and then trying to, oh, I got a bunch of hay, where are the needles? You start with, what needles do I want? Okay, and how do I get just enough hay to find that many needles, right? And what's the hay sifting model that I'm going to use to get to the needles? And if you start there, you end up with a lot less hay and a lot more needles at the end of the day. And that's really what we're trying to do, is have smaller models that are much better at answering very specific business questions and do that in an efficient manner. $8 a query is not going to work in a lot of cases. So you're never going to get ROI out of it that way.
So it's almost like a hierarchy of thinking is, what are the problems I'm trying to solve? What models do I use to answer those problems? And then what data feeds those models?
Exactly. Okay. And then it goes through an iteration. Really, there's this model development lifecycle, which is kind of like software development lifecycle. We're calling it MDLC. But the difference here is that in software development lifecycle, I can get to a product planning session and road mapping session and Q3 for a company's software and say, yeah, next year our budget's down, so we're only going to add these features. We're not going to do that much more development. Well, the problem with the models is that they're living things. When the data changes, they become not so valid anymore. When we switched from the Indy cars that didn't have a hybrid engine to having a hybrid engine, wow, now we're doing battery management. That's very different. All the data kind of changes. If I go on and just use my gasoline-only engine data, I'm not going to get the same answer. So we do have to iterate now, and our budget cycles, our design cycles, and everything have to kind of change to meet this new paradigm where you have this kind of living thing out there that needs to be fed and maintained in order for it to do its job right. So I think that's kind of a cool development in this whole thinking of how we engineer software, how we engineer models out there. So we develop the model, we deploy it, we put it in the wild, and now we have to see how it performs and constantly re-benchmark it and revalidate that model to make sure it's valid based on the data that's coming in now.
So how did you get started in all this? You have Zapata, and where does the idea of this company come from, and what's kind of the core catalysts for making it become its own thing?
So we spun out of the quantum algorithms lab at Harvard in 2017. So 6 of us took the technology out of the Harvard quantum lab there. We had really good linear algebra, really good high-end math, let's just call it that, right? Where we knew how to solve quantum chemistry problems and quantum physics problems, which are some of the hardest multi-dimensional spaces to do math on, right? Like, this electron's not just here, it's on the other side of Andromeda, and you have to take that into consideration when you do your calculations, or your GPS doesn't work, right? The statistics kind of matter. It's here and here and here and here, but it's more here than it is there. And that kind of statistical framework and world that we lived in is really hard. So now we're developing quantum computers that can do that natively really well. But the math behind that at the end of the day is linear algebra. That's what it is. It's really powerful statistical algorithms that can work in that kind of a space. And so taking those algorithms and those ways of doing things and applying it to industrial areas was really the vision from the very beginning. Now, we can use that to do quantum chemistry for materials development, and we can use it for a bunch of other things. But one of the key things we realized at the very beginning of this is, wow, generative modeling. Back in 2017, before Sam Altman even had a for-profit entity with OpenAI, we're like, generative modeling looks a lot like a molecule. I know that sounds weird, but a molecule is this electron that has some fuzziness next to this electron that has some kind of fuzziness. It's neither here nor there nor anywhere because of the uncertainty principle. Now I need to take all those things into consideration to figure out how this molecule is going to bind to that molecule, and what that's going to look like, and try to be predictive of that. Well, molecule looks a lot like a language model or other models of things like what we're doing with generative modeling, like DALL-E, a program like that. You can go to DALL-E and say, draw me a purple polka dotted cat with no tail. And it will do that. And you say, well, how's it able to do that? It hasn't trained on pictures of purple polka dotted cats. At least I hope not, right? But what it has done is seen a bunch of cats. And it's been able to generalize what is cat. And what is cat differentiated from what is dog, right? And that generalization is the first thing. So it's able to find a statistical model of, okay, cat is kind of this four-legged thing. The head is about this big compared to body, but not that big. That when it gets this big, it's not cat anymore. And when the tail's that long, it's not cat, it's raccoon. And so it's able to find these generalizations of these parameters that are all statistical. A paw can be this big, but not that big. It'd be kind of that big, but not weird, right?
Sure.
Not too weird, or it's not cat anymore. But it is also expressive enough, like these quantum systems, to say, yeah, it could be on the other side of Andromeda. Thankfully, this atom is in my fingernail and not on the other side of Andromeda, but it's more here than there. But in reality, it actually is somewhere else too at the same time. It's just less there than here. And that's really what this modeling does. So we were able to correlate what we do with the molecules and atoms, right, into what that looks like. And so we were able to apply that math into making better generalizations and making better predictions or expressions off of those generalizations, so that we can do things like no tail cat with purple polka dots better than the models that we're using now in DALL-E and some of those other diffusion or other types of models. So using the quantum statistics that came out of that was really the insight we were able to use very early on. Our first patent in applying quantum math to generative AI was in 2018, our first patent application. So we were doing this from early days. It was kind of hard to say we're a quantum company that does generative AI in 2018. It's kind of like talking about Siri in 1998. So this was that wasn't new for me. Like, yeah, you're going to talk to your phone and you're going to ask it what the weather's going to be like tomorrow. Well, why don't you just watch the weather? That's what I got back then. And this was kind of like that. Well, why would I want to generate fake pictures of stuff? What's the business model for that? No, it's not just fake pictures of cats. You can generate a fake picture of a bridge that actually works and engineer stuff. And like we were talking about in the racing example, a slip angle of a car. Okay, how? I don't get it. So in some ways, we were a little bit ahead of our time. Thankfully, the OpenAI project and these kind of things and that coming out here has made people realize that there's a lot of power in this generative capability. I think it's gone too much to the language side and generating bad marketing copy. And I think it can be better used in some of these creative engineering types of applications, is my own personal opinion.
If it could write better marketing copy, my job would be much easier, or I wouldn't have a job. So happy to see that it's still not quite there yet. So earlier we were talking about lots of small kind of agent models versus one big coverall model. Are you doing the agents? Or are you doing the higher level, like higher up in the stack? How does that all play together, and what does that look like?
So in our company, we have a platform that allows us to do a full stack development cycle with ensembles of these agents. So we're able to develop an agent and an ensemble of agents and have them work together. In Andretti, we have 65 agents, if you will, these small models running on two A100s at the track real time with real time streaming data doing inference live, which is pretty cool. And we have this orchestration tool, Orchestra, it's named, to be able to do this kind of orchestration of ensembles, to build these ensembles of agents, to then coordinate these models and have them work as ensembles, as an orchestra, to create outcomes and to be predictive and things live.
Yeah, that makes sense. That you wouldn't necessarily want to have a checklist of all your different agents and be like, oh, call the suspension agent and the tire coefficient of friction agent and all that. You just want kind of a single input output, feedback. That's what's most useful.
Exactly. You want, a platform that allow you to do that and use a UI at the end of the day. You can develop, any kind of UI tool. Tableau can be integrated, other things to give you a graphical, or even use an OpenAI agent to query those things and then give you a natural language answer. So that you can do things like, hey, tell me what my predicted lap time will be for the next lap. And have that thing go ask all the other agents, like the tire degradation and the timing agents to give you that answer.
Well, I could talk, I think, with you all day on this, but we only have a couple minutes left, and we like to do some lightning round questions at the end of this.
Okay.
One of my favorites is you've been in this space and ahead of the game for a couple decades now. What are some instances that you've seen either in real life or even in like pop culture fiction movies that have really gotten this AI thing right, and what are some that have maybe really gotten it wrong?
Oh, that's a really really good one. I think the HAL thing and the Star Wars computers and the Star Trek, particularly great computer, have gotten it wrong in the sense that I alluded to, that they this monolithic thing that has all the data and all the answers for everything, and that's what the thing is. Maybe that's the idealism that we've had. I think the technology's fallen short of giving us, computer in Star Trek. And I think that set the wrong expectations, that we're going to get this HAL-like, super intelligent, human-like thing, as opposed to a tool that we can use for specific tasks.
There's got to be something psychological. Like on the engineering side, I think about, different types of test gear for different problems. But as a consumer, as a human, I just kind of want one interface where it's like, turn up my thermostat and preheat my EV battery and, remind me to start the oven in 20 minutes.
Yep, I think so. And I think, some of the other stuff that you see in the science fiction kind of drama sense of like being predictive of people's behaviors and this kind of dystopian thing, there is some of that danger, I think, that's out there. Like we are now able to, with the big data, really know a lot about a consumer. I think we alluded to that in the conversation. Some of that stuff isn't far from the truth. We're able to solve crimes pretty quickly. And if it gets to be too much of a big brother state, we've seen this like in China, for a good reason. They were able to find somebody committed a terrorist act in like 8 minutes because of all the cameras and whatever in a country with 1 billion people. That's pretty cool, but it's also, okay, that's an authoritarian state that has all that information. Do I really want that? So some of that dystopian stuff does have some rooting in reality.
Is there anything that scares you about where AI is going, and anything that we should, as a kind of a general call to action to the population, do about it?
Well, I think it's more about how people use it. I think that keeping our privacy and this legibility of government is what it's called, when they can see into what people do with their money and what they do with their purchases and what they do. At the end of the day, that becomes control. And I think we've become kind of frogs in slowly boiling water a bit, in ceding our control to big tech companies and to governments, not in a paranoid way, but we've just done it because it's convenient, right? I'd rather have all my passwords in one place. I'd rather have search history here, so it's really giving me relevant search things. I like my Expedia hotel recommendations to be this, but now it knows exactly what kind of hotel I want, where it is, and it has data on me. How could that possibly go wrong? Right? If a government did that, And we've seen that, even rather unsophisticated things like, lists of, people's genealogies were used in Germany to kill people. That's not an extreme example of how things can work when a government has information and wants to control. So kind of there is a, be careful what you wish for with this technology. I'm not, conspiracy theorist on either side of any kind of political spectrum, but I am really, I come out of a tradition where people have been killed over time because of who they are, and that makes me a bit sensitive to how things might be misused in the future. I think the biggest mistake we could ever make as human societies is think, oh, that would never happen here. That could never happen here. And I think it behooves us to get out in front of that and think about all the ways that it could be misused. If the wrong people in charge with power, absolute power corrupts absolutely, but even a little bit of power can be a really corrupting thing and can be misused. So, I think it really is legibility of government, legibility of body politic on citizens and how they do things. So, AI by itself, maybe not so much. But AI and data legibility and, a national digital currency that's all you can use to buy things with, that now we know every single purchasing behavior that you do and everything. Now we have total control over you because I can turn off your ability to buy food.
Sure. Yeah. That's tools are scary, and nobody thinks they're going to be the one whose table saw slips and, slices their hand, right?
Exactly.
On a maybe a lighter note, and in about 30 seconds, if you could wave a magic wand and have AI do a thing or solve a problem in the world of AI ML, what would you kind of magically solve or fix or change?
I think multimodal, for me, I'm kind of busy. Multimodal suggestion of my calendar and time management would be really useful. Like, I think, we can have it do calendar appointment reminders right now. But really complex queries, I really would love that. Like, hey, I'm going to Europe next week. I'm going to be in this city and then that city. Where should I be with my hotels and whatever based on my preferences? Like, that would be really cool. And I want a hotel with a pool for my workout and blah, 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 but under this amount of money and blah, blah, blah. This is my budget. Yeah. And go.
I'm in.
That would be really cool.
Well, thank you so much for your time. This has been really enlightening and interesting.
I hope it's been helpful, and thank you. This has been a really interesting conversation.
That was Christopher Savoie, founder and CEO of Zapata AI. Thank you to Mouser Electronics for sponsoring all the keynotes this week. This is the last you'll see of me for this Industry Tech Days 2024 event, but we have some other great live sessions coming up today right after this. Thank you for joining me for all the keynotes this week. It has been an honor getting to learn alongside you. I'm Daniel Bogdanoff, and I'll see you next over on the Moore's Lobby podcast, or maybe some of the live sessions later today.